In one of the earlier videos, I was listing off some quantities that are vectors and some quantities that are not vectors, that are called scalars. And I mentioned that forces are a vector. So in this video, we're going to take a look at what that means. I'd like to start with another look at the law of inertia, which says that objects do not experience any delta V unless they interact with another object. In that video, this cart was interacting with a string that pulls it to the right, yet it experienced no delta V. This cart was also interacting with my hand, pushing to the left, yet it experienced no delta V from the hand either. The law of inertia says objects do not experience any delta V unless they interact with another object, but we're going to have to clarify that wording. Every interaction can result in a delta V, but not every interaction actually does. It depends on what else is going on. Notice once the interaction with my hand is removed, the interaction with the string does result in a delta V. And the longer time it keeps pulling, the more delta V the cart experiences. That brings us to some key terminology. Objects do not change velocity unless an unbalanced force acts on them. And the equation that governs that relationship is force times the amount of time elapsed that the force is applied to the object equals the mass of the object times the change in velocity of the object. And the amount of delta V the object experiences then depends not only on the magnitude of the force, but also on the amount of time for which that force is applied, and also, of course, the object's own inertia. Let me manipulate this equation just a little bit. If you divide each side by delta t, then the delta t divides out on the left, and you're left with the force equals the mass times delta v over delta t. But what is delta v over delta t? It's acceleration. So force equals mass times acceleration. And this equation may look familiar to some of you. This is a fairly famous physics equation, and in either format, it's called Newton's second law. The units for measuring force are called newtons, and 1 newton is equal to 1 kilogram of mass times 1 meter per second of acceleration. I'd like to show you what happens if we do a little experiment with this cart. We're going to pull the cart to the right with the string. We've got it set up so we're pulling with the exact same amount of force each time, and let's watch how the acceleration of the cart changes from one trial to the next. In the first trial, the mass of the cart, it's an empty cart and the mass is 500 grams. Here we've added 500 extra grams. Now we're up to 1 kilogram of added mass plus the 500 grams of the cart to begin with. Do you see any difference in the motion of the cart now? Here the cart and added masses have a total mass of 2 kilograms. The same string pulling gives less delta V. The acceleration of the cart is the slope of the velocity versus time graph of the cart that we made while we were conducting the experiment. The acceleration of the empty cart, which was a mass of 500 grams, the acceleration is 0.4008 meters per second. When we added 500 grams to the cart, the acceleration was 0.1802 meters per second, so it went down. When we added another 500 grams, the acceleration went down to 0.1014 meters per second, and when we added another 500 grams, the acceleration was down to 0.06289 meters per second. Remember, these were all caused by the exact same amount of force acting on different amounts of mass. So the effect we're seeing is that the acceleration is dependent on the force applied, but it's also inversely proportional to the mass. Let's clear up that law of inertia a little bit. Objects do not experience any delta V unless they experience a net force, meaning that the total sum of all the vectors, of all the forces acting on an object must be added up in the manner that we've learned how to add vectors. If all of the forces add up to 0, then the delta V on the object is 0. But if all of the forces add up to a net force that is anything not zero, then delta V is also not zero. Let's be clear about what we mean when we say that we must add up all the forces acting on an object. So in any given situation, step one, you want to identify all the forces that you recognize in the problem. So for example, the force of my hand and the force of the string were acting on this cart. We also had the force of gravity. I didn't mention that during the experiment, but we know it's there, and we do need to account for it. Well, if the force of gravity is acting on the cart, why is it not falling? The track is holding it up. There's contact between the cart and the track. And for now, I'm just going to call that the force of the track. When you go to label these forces, in the next video, we'll talk about how each of these may have a special name that physicists use to refer to them. But when in doubt, if you use something descriptive like force of track and force of hand, as long as it's clear what you're talking about, it can still be fine. The next step you'll take is step 2, draw a free body diagram. And we're going to practice this in a following video. But for now, let me show you how a free body diagram works. The first thing you want to do is draw a dot or a box to represent the object you're talking about. So this is the cart from the previous slide. It doesn't have to look like a cart because we're just using this to analyze all of the different forces. When you draw a free body diagram, you want to draw every force that's acting on the object as though it is a vector emanating out from this dot. Even though the forces are coming from outside of the object pushing in on the object, we don't want the arrowheads pointed in, we want them all pointed out. That's not because this free body diagram is supposed to represent how the forces are acting on the object in a necessarily very visual way or an intuitive way, but it's because we're going to use this to add the vector forces together. And so we want it to be that all of the forces are starting in the same place. The first force I'm putting on there was the force of the hand, and I'm making sure that it points in the direction that the hand was applying a force. The second force I add is the force of the string. The third one is the force of gravity, and the fourth one is the force of the track. It was yellow on the picture of the cart. I changed it to blue here because the yellow wasn't showing up very nicely. Notice how the force of the hand and the force of the string appear to be about the same size. They should, because they were known to be about the same strength. I know they were the same strength because when they added up, they resulted in no net force. I know they resulted in no net force because the cart experienced no delta V in that direction. I don't know if the force of gravity is larger than the force of the string or the force of the hand right now. That might be something I could calculate, but to start with, I don't know. What I want to make sure is that the force of gravity and the force of the track are about the same size because I know that they have to be equal amounts. The cart was not accelerating up and it was not accelerating down, so these two forces also have to add up to 0 in the y direction. The next thing I would do is I would list all of the values that are known. The forces that I've got on here are known values, and if I know the amount of any of these, I would put it on here. The important thing to remember right now is if you start listing any other known values, like a delta y or an acceleration or something, it should not be on the free body diagram. You can list those things off to the side, but because you can't add different types of vector, like you can't add a displacement to a velocity, and you can't add an acceleration to a force, you should not put anything except forces on this free body diagram. The next step would be to add the forces that are in the x direction and add all the forces that are in the y direction to one another. And again, we will definitely do some examples of that so that you can see what we're talking about. Right now, I'd like to define forces more clearly. A force is a vector that is representing the interaction between two objects. Both objects feel the force as either a push or a pull. If I'm pushing on the cart, then I feel that cart pushing on my hand. That's a contact force that I'm aware of in my fingers. Gravity is pulling down on me, And I told you in the very beginning that it's not a good idea to refer to it that way, because we want to instead say an object is pulling down on me, the earth is pulling down on me, and gravity is the way in which it is doing it. I'm also pulling up on the earth. That's not immediately very obvious because I'm so much less massive than the earth that I don't affect the earth. When I trip and fall, it may feel like the earth is rushing up to hit me, but in reality, an observer would be able to identify that I fell and the earth didn't move. That's only because I'm so small, we don't see any effect. We don't see a delta V on the planet. We do see a delta V on things like planets when we see them interacting with other objects that are of comparable size and mass. So having seen that definition, that takes us to something called Newton's laws that you've probably seen before. I'm not going to ask you to recite these ever, but you will have to understand what Newton's laws mean. If you don't understand these, that's a good sign that you don't understand how forces work. So Newton's first law is the law of inertia, which we've already stated. I'll come back to that. Newton's second law is an equation. It's usually written as F equals ma. It can also be written as the net force, delta T, equals m delta V. Newton's first law is really just a special case of Newton's second law. The law of inertia says that an object won't experience any delta V unless it is experiencing a net force. So Newton's first law is just a way of saying, with Newton's second law, if one side of this equation is 0, then the other side also has to be 0. The reason Newton bothered to make a first law that came before the second law is it was really his way of saying, if you don't understand inertia, then you need to go study Galileo's experiments before you try to understand the rest of what I'm working on here. Newton's third law is just the definition of the force, the implication that if a force is experienced by one object, whatever the second object is also experiences the force. So you can't have a force experienced when an object is by itself. You need a second object to cause that force. And then both objects involved experience that force with the exact same magnitude, but in exact opposite directions, like was shown on this slide. Okay, so Newton's first, second, and third laws, and our next video will be a lot more detail about the definitions of the different types of forces we're dealing with and how to do more complicated free body diagrams and how to apply them to solve problems. So that's just a little picture of Isaac Newton, and I'll see you in the next video.